Part 1. Please find a quiet place to sit or lie and to listen to this audio. Once seated or lying, close your eyes. Focus your attention on your breath. When you are ready, inhale slowly. Let the air fill your lungs. And then exhale slowly. Let the air escape from your lungs. Inhale again, and then exhale again. Notice how your stomach rises as you inhale and then falls as you exhale. Rises as you inhale and falls as you exhale. And if your mind wanders, don't be concerned. Just gradually shift your attention back to my voice. Part 2. Imagine that you have inserted some food into your mouth. Perhaps some bread or a carrot. Visualize your teeth slicing the food into small pieces. Imagine your tongue and saliva converting these pieces into soft mush. Now imagine that you have swallowed this mush. The food now falls down the esophagus, sometimes called the food pipe. However, unlike a person who dives from a ledge, the food does not fall freely. Instead, smooth muscles in the esophagus contract and relax, contract and relax, contract and relax. And because of these contractions and relaxations, the food seems to plunge in small bursts. That is, the food plunges and then stops, plunges and then stops, many times before reaching the stomach. Part 3. Now for a moment, imagine your stomach feels full. You feel you could not possibly eat any more. How do you know that you could not eat any more? Your stomach and intestines cannot tell you they are full. After all, your stomach and intestines do not speak, and they're not conscious, they're not aware that they are full. Instead, somehow your body must convey this information to your brain. Your body must use some mode of communication to inform your brain that you are full. So how does your body communicate this information to your brain? Your body obviously does not communicate with words. Instead, your body communicates with chemicals, specifically hormones and neurotransmitters. The stomach communicates with a molecule called ghrelin. The duodenum, the first part of the small intestine, communicates with molecules called CCK and OEA. The pancreas communicates with insulin, and your fat cells communicate with a molecule called leptin. Now at this stage, you don't need to remember words like ghrelin, CCK, OEA, insulin, and leptin. You merely need to realize that your body uses these chemicals together with other processes to communicate to the brain. Part 4. To understand how these chemicals operate, imagine that food has entered your stomach. Your stomach now feels full. How does your stomach convey this feeling to the brain? The stomach actually uses several mechanisms. First, the stomach uses the vagal nerve. The vagal nerve is a nerve, or set of neurons, that travels from many parts of the body to the brain and back again. Indeed, the vagal nerve is actually the largest nerve in humans. Actually, the vagal nerve does not resemble just one long hose. Instead, the vagal nerve more resembles a complex tree with lots of branches. Specifically, imagine you can see inside your brain and body. Like the other cranial nerves, the vagal nerve begins in the bottom section of the brain called the medulla. You can then imagine this nerve, like the trunk of an upside-down tree, travel down the neck, the chest, and the abdomen. At various points, various branches emanate from this nerve and travel to the heart, the lungs, the stomach, the intestines, and the pancreas. Now focus your attention on where the vagal nerve ends at the stomach. Tiny branches of this nerve cover many parts of the stomach. And imagine the ends of this branch resemble small onions. And whenever the stomach is full, these small onions are stretched as well. And once stretched, the nerve begins to ignite action potentials. So you can imagine sparks of energy, like electricity, travel up the nerve and back towards the medulla at the bottom of the brain. This activity in the medulla is then relayed to other regions of the brain. The brain thus learns the stomach is distended. The brain thus suspects the stomach must be full. Besides the vagal nerve, the stomach can also communicate with a hormone called ghrelin. In particular, the stomach, when empty, produces ghrelin, a protein that resembles a small coiled ribbon. You might be able to imagine segments of ribbon continuously emanating from the cells that line the stomach. Then imagine another structure like a revolving door shifting this ghrelin into a blood vessel. The ghrelin then floats in the blood and drifts to all parts of the body. Eventually this ghrelin, these segments of ribbon, drift towards a specific region of the brain called the hypothalamus, a region that contains about 15 distinct clusters of neurons, like small jelly beans, located a few centimetres behind the top of your nose. So what is the effect of this ghrelin in the hypothalamus? In essence, ghrelin says to the hypothalamus, "My stomach is empty, so I must eat." Of course, ghrelin does not actually articulate these words, but ghrelin actually attaches to a receptor in the arcuate nucleus, a cluster of cells in the hypothalamus. But the words, "my stomach is empty, so I must eat," captures the role of this hormone. After you eat, your stomach distends from the weight and bulk of food. Interestingly, the stomach, once distended, no longer releases this ghrelin. The concentration of ghrelin in the blood diminishes. The blood, in essence, is no longer teeming with these coils of ribbons. Hence, the arcuate nucleus in the hypothalamus is no longer instructed to eat. Your appetite wanes. You do not feel as hungry. Part 5. Now imagine the food or mush in your stomach propelled into the first section of your intestines called the duodenum. The duodenum extracts and absorbs many of the nutrients in your food, such as fats and amino acids. Once the food or mush arrives at the duodenum, cells in this region produce a hormone called cholecystokinin, often abbreviated as CCK. You can visualize this CCK as similar to tiny keys floating in the bloodstream. And these tiny keys generate two effects. First, the CCK, that is these keys, attach to a small circular muscle resembling a ring between the stomach and duodenum called the pyloric sphincter. As a consequence, this ring of muscle contracts, and so food therefore is more likely to remain in the stomach. The stomach feels fuller. The CCK also activates the vagal nerve, the nerve described before that resembles an upside-down tree. And this nerve also travels to the hypothalamus as well. And perhaps you can imagine sparks of energy beginning in the intestines and ending in the brain a few centimetres behind the top of your nose. And these sparks of energy prompt the hypothalamus to generate more CCK in this region. Maybe you can imagine CCK resembling tiny keys sprouting for the hypothalamus as well. And this CCK somehow tells the brain the person is full. So therefore, after eating, CCK is released both in the duodenum, just past the stomach, and in the brain or hypothalamus as well. In addition to CCK, the duodenum releases another chemical called OEA in response to food. And in particular, the duodenum releases this OEA when fat enters the duodenum. Specifically, the effect of OEA is similar to the effect of CCK in that the OEA also activates the vagal nerve. Part 6. Food does not only affect the release of hormones from the stomach and duodenum, but also affects the release of hormones from the pancreas. The pancreas is an organ resembling a fat carrot wedged somewhat under the stomach. Cells in the pancreas called beta cells release a vital hormone into the blood, and this vital hormone is called insulin. To illustrate, imagine mushy food travelling from your stomach to the duodenum, and some of this food is digested to generate glucose, the main constituent of jelly beans, for example. Perhaps you can visualise this glucose as tiny specks of sugar. And this glucose, these specks of sugar, are then transferred into the blood. Maybe you can imagine something like a revolving door, shifting this glucose from the duodenum to the blood inside the blood vessels. This blood now, teeming with glucose, resembling tiny specks of sugar, then travels to the pancreas nearby. Now imagine that once the glucose approaches the pancreas, the beta cells produce more insulin than usual, or a hormone that you can visualize as bunches of small streamers. The insulin then drifts in the blood, and insulin finally attaches to receptors on most cells, probably like keys attached to locks. And once attached to these receptors, the glucose, the specks of sugar, can then enter cells. Cells can then utilize the glucose to generate and use energy. Without insulin, glucose could not enter cells, except brain cells. And without glucose, the cells cannot perform their functions. Besides glucose, even thoughts about food can increase the release of insulin from the pancreas. Therefore, even before meals, the pancreas tends to produce insulin. And recently scientists have discovered that insulin can also diminish hunger. That is, insulin can attach to special receptors in the brain, and once attached, the appetite subsides. Part 7. Most of these hormones, like ghrelin and CCK, depend only on whether the person has consumed enough food in the last hour or so. If the person has eaten a large meal, these hormones diminish appetite. If the person has not eaten for hours, these hormones will increase appetite. But now imagine a man with a gaunt and scrawny body who has been ill and has eaten minimal food over the last month. If this man now eats a meal, hormones like ghrelin and CCK will diminish his appetite. But actually, this man still needs to eat more to counteract the inadequate food over the last month. In contrast, imagine another man with layers of fat covering his body. If this man has not eaten for hours, these hormones like ghrelin and CCK will increase appetite. But actually, this man does not need to eat a lot more, because he can use the reserves of fat in his body. Fortunately, the degree to which we eat depends not only on the amount of food we just consumed, but also on the level of fat in our body. So how does the level of fat in our body affect appetite? Well, to answer this question, imagine that, using a special microscope, you could observe the fat cells in your body. And these fat cells are like small little blobs. Perhaps you might imagine these small blobs in the fat around your own stomach or around your thighs. And these fat cells each produce a hormone called leptin. And maybe you can visualize this leptin as tiny bacon bits. This leptin, or these bacon bits, then enter the blood and travel around the body. Eventually this leptin reaches the brain, and specifically the arcuate nucleus, the region in the hypothalamus located a few centimetres behind the top of your nose. In essence, leptin instructs the arcuate nucleus to diminish appetite. So maybe you can hear leptin resembling tiny bacon bits telling the arcuate nucleus, the body is full of fat, we need no more food. The body is full of fat, we need no more food. And if individuals had formed many fat cells, in other words, if they are fat, they tend to produce more leptin, diminishing appetite to a greater extent. In short, many hormones such as ghrelin, CCK and leptin provide information to the arcuate nucleus. Specifically, these hormones indicate whether the person needs to eat more food. And the arcuate nucleus then regulates the level of hunger that people feel.